Hello, and welcome to Class 1 Remote Sensing Overview for the course Photogrammetry, Remote Sensing, and Analysis at Warren Community College. Just to give a little highlight or a little definition, remote sensing is a very fancy word for meaning taking imagery from the sky. So it could be from outer space, from an airplane, from a drone. And what we're trying to do is gather information or acquire information about an object or phenomenon without ever making physical contact with it. So thus, if we're in space and we're trying to capture imagery of the Earth, we're obviously not going to be on the Earth at the same time. And then it's in contrast to on-site observation, especially on the Earth. So we kind of call the terrestrial view that ground view that we have when we're standing on the ground. But this aerial view, or a view from outer space or airspace in some way, shape, or form, we're going to refer to as remote sensing. You should know that it's used in many fields: geography, land surveying, most of the earth science disciplines, hydrology, ecology, meteorology, oceanography, glaciology, geology. And it has military, intelligence, commercial, economic, planning, and humanitarian applications. Remote sensing has really taken off with the advent of the era of the drones or their unmanned aircraft systems, especially the small unmanned aircraft systems. Whereas in the past, capturing data could be so expensive. Okay, you might have to rent a satellite. Think about the cost of that. Or you might have to hire a pilot, rent his aircraft, and have him or her go through and gather your imagery. Now, for $400, you can basically throw a drone up in the air and capture a lot of what you used to have to pay a considerable sum of money to do. So remote sensing has become a very important component of the unmanned aircraft industry. So remote sensing refers to the use of satellite or aircraft-based sensor technologies to detect and classify objects on Earth. Current advances in unmanned aircraft system technology are allowing the practice of remote sensing to expand, and it's expanding, as I said before, exponentially. So it's really important to think about this. Remote sensing has been around for a long time. It's a very important part of data gathering. But now, with the advent of commercial off-the-shelf drones and the ability to use them with some sophisticated software that we'll talk about in a few minutes, it really has become an interesting and compelling way to gather data that is often worth a considerable sum of money, but captured and acquired at a much less expensive and a much more cost-effective manner. So there are some kindred technologies or some related technologies, and here what you're seeing is we're starting to see how images might be captured in the picture by a drone, and those images would refer to an exact geographical location on the Earth, and we would create imagery from this. But we can use this technology in a number of ways. We can bring it into geographic information systems, such as the ESRI products. We can bring it into photogrammetry software systems like Pix4D or Drone Deploy. And we use GPS or global positioning systems to kind of differentiate the pictures and to place them on a place on the planet rather than just existing in the abstract. So we should remember that the greatest remote sensors that you'll ever experience are the internal sensors of your eyes, okay? So your eyes are the great remote sensor. We're going to replace your eyes for the sake of capturing imagery with a camera or multiple kinds of cameras that we'll talk about in this overview. We're going to replace your brain, which would process what your eyes see, with a computer in the unmanned aircraft system. And what we're looking at is the data, and the analysis is the interpreting of what is seen. So you know this because we've all seen things and then our recollection goes. This allows us to capture the information from an aerial viewpoint that then allows it to exist as long as we digitally keep it. So what is remote sensing again? It is this capturing of the imagery from above, but it's extremely important. What I'd like you to do now is pause this video for a second, go to YouTube, and in the search box, just type remote sensing. In this case, it should be the first through fifth video that pops up. It will look like this, and it'll be say, what is remote sensing? Okay. And you can see this is put out by NASA, and they're going to explain remote sensing and give you some great examples. And mainly because it's put out by NASA, you're going to get a lot of outer space examples in this, but it's going to give you a good sense and a good video imagery of what you can capture and how it's used and what the application would be. We're going to bring it down a lot of levels from outer space to our own atmosphere and planet and how we get closer with drones and see how that will be. But please pause now and watch your 4-minute and 21-second video called What is Remote Sensing on YouTube. And I think you'll get a lot out of this, and it'll help really explain some things that we're going to go over in a few minutes. Welcome back. I hope you enjoyed that video. So one of the things we have to talk about is when we're doing remote sensing, we're not using our eyes. We're using some kind of technology, often a camera, or it could be what's known as a red, blue, green RG, or red, green, blue RGB camera that picks up those visual imagery of those colors. It might be an infrared camera, which again, you would not be able to pick up with your eyes. It could be a multispectral or hyperspectral camera, which again has colors and variations in it, which you would not be able to see with your eyes, but can assist you in a lot of the work. So what we're really doing is we're using the electromagnetic spectrum to capture data in visual orientation that we can assist us in all kinds of applications, in inventory. So for instance, if I had massive piles of coal and I needed to know how much was there, I could fly a drone over it, capture it, bring it into an application like Pix4D, and literally compute the volume of that without having to ever go out there and use other methods. So that can be a very cost savings or cost effective way to do that. We talk about mapping. When we talk about drone mapping or mapping, we're talking about a photogrammetry where we're trying to recreate to the most accurate sense possible the Earth, the things and the phenomena on the Earth at the time. So we're creating a map, often two-dimensional, although I will say with this technology, we can also do three-dimensional things, and we'll give you an example of that later. Monitoring the Earth's resources. So that's what the video you just saw kind of talked about, watching things like, is the planet warming? Where are the resources? Are the polar ice caps melting? Where is that water going? And we can look at this over time, longitudinally, and look at exactly what's going on our planet and keep digital references throughout history that can be used throughout time, and to ensure that as future generations come, if there is recycling of the Earth's atmosphere, if there are changes, we would be able to pick these up and notice them much quicker because we have a constant monitoring that's going on. Police can use this in accident reconstruction. We can literally fly an accident in minutes, what might take people on the ground using a terrestrial camera an hour to do. We can do in about 6 minutes, and we can reconstruct with a 3D model from that. The one nobody likes is the surveillance aspect of it. We do know that people obviously don't like this. It's usually larger drones that are used this way, and we've seen some of this where there's been some drones used over U.S. soil when Border Patrol, etc. From a general standpoint, always be aware if you are studying drones or you're looking at it, probably one of the biggest public kind of scenarios or concerns or public thoughts about the use of drones especially is worrying about, will I be surveilled? Will my privacy be invaded? So these are things you want to keep in mind. Probably not the most publicly accepted use, but certainly a use for remote sensing, for drones, for aircraft, etc. This notion of surveillance. Search and rescue, much more generally accepted phenomena, and that's the idea that we can use this looking from above to find something that's missing. So, you may see the police force use this in infrared cameras. If you were to go through the Warren program, you'll use a program called Locate, LOC8. And what Locate does is look at pixels to differentiate from the natural phenomenon there to help find someone quicker. So there are numerous ways of doing this. I often tell students, if you want to practice search and rescue and you're not a member of law enforcement, the best thing you can do is look for people's missing pets. That might be something that law enforcement wouldn't be involved in. You wouldn't be in anybody's way. You wouldn't be violating any rules, laws, etc., interfering with the proper duties of first responders, but you would be able to basically do about the same kind of work and get a sense that that's something you would like as a career. And progress reporting, think a construction site, large developments. You could literally take numerous shots and then report back to whomever. So these are just a few. I mean, we're seeing this used, remote sensing, using drones in archaeology, in capturing existing infrastructure in case it ever had to be recreated, forestry. The sky's really the limit. And if you can think of an industry, you can probably think of a way they're going to use remote sensing and drones in that industry. So these are just a couple examples. We probably want to understand that what we're using is the electromagnetic spectrum, and we're capturing imagery on the ground. So in the electromagnetic spectrum, you can see that the wavelength's different all the way to AM radio waves, which you're more familiar with. You have an AM station near you. You can plug in the numbers. FM, the numbers get a little smaller. TV, your numbers get a little smaller. Your waves get a little smaller as well. Then there's infrared, which you really can't see. Ultraviolet, you cannot see. Radio waves, you can't see either. X-rays or gamma rays. So there's only that really small part of the electromagnetic spectrum that really is visible light, and that is your red, your green, your blue, and your color combinations there. And what happens basically is as the sunlight and the rays of the sun hit the planet, some are scattered, some are absorbed at the planet level, but many are reflected, and these reflections are what we're picking up. So we can pick them up from a low altitude drone, a low altitude single engine plane, high altitude jet planes. You might be familiar. You can Google things like spy planes and see these. We've been using remote sensing that way. From the space shuttle, which goes up to a certain beginnings of outer space, to Landsat, Moss, Spot. These are large satellite systems used for remote sensing that we'll talk about in a later video, and then geostationary satellites as well. So as you can see, you can imagine that your reflection versus what's absorbed and scattered is going to differ. So you're going to get some of your best imagery closest to the ground because you have less scattering using a drone. So drones have become a really go-to mechanism for collecting this kind of data because they work well with the electromagnetic spectrum. So let's talk a little bit about this and watch another video. In this one, you're going to get a real explanation of everything I just kind of shared with you with the electromagnetic spectrum. You're going to see how the reflection occurs. You're going to see what's picked up by various instruments. So let me say, back to YouTube, go to the search box and type in mapping the invisible. And if you type that into the search box, you should get one that says mapping to the invisible, introduction to spectral remote sensing. And this is going to go over many things in the spectrum. Okay, go over how your camera actually takes a picture and talk about the lights and the light reflection. This is about a 6-minute and 6-second video, but you will get a lot out of it. It'll explain a lot of things in 6 minutes that if I was to sit here and kind of go PowerPoint slide by PowerPoint slide would take much longer. So for the efficiency's sake, let me suggest you go and watch this video now. Welcome back. I hope you enjoyed that video as well, and I hope it really gave you something you could think about and apply in this kind of overview. So let's talk a little bit about this, about the two processes of remote sensing: data acquisition and then data analysis. So when you're doing the remote sensing, when you're capturing the data, that's when you're going to use your aircraft, satellite imagery, etc. And your analysis will use some other kind of software, whether it's GIS software, it might be CAD, could be Pix4D, Drone Deploy. There are numerous softwares out there. So when we talk about data acquisition, what we're getting is the propagation of the energy through the atmosphere. That's that light. All right. So those electromagnetic wavelengths, whether they're radio waves or they're visual infrared, they're going to go through the atmosphere and they're going to propagate. Now, be aware that a lot of these things do not propagate through water. So that's one of the things we kind of often talk about. We can pick up water imagery from above, but what's beneath the water we often can't get. So just kind of keep that in mind of what you can propagate. You can propagate through space, through our atmosphere, but you're probably not going to be able to propagate using the electromagnetic waves through water itself. But what you do get will be very valuable. And again, remember this concept, because we're going to come back to it, of what's reflected versus what's dispersed. What makes it through, what's lost, because these things do happen. As you saw from the video, there are color and energy interactions that occur with the Earth's surface. So you want to keep that in mind as well as you're kind of thinking about your data acquisition. Then you're going to get that retransmission through the atmosphere. Depending on how high you are, is going to affect how the quality, and depending on the level and sophistication of your sensor itself. And usually sensor, we talk about some kind of camera or digital acquisition device, okay, that we can get information from. And then let's think that we have airborne and spaceborne sensors. So they're going to be slightly different. You're obviously not going to use a small camera from outer space. You're going to use a much more sophisticated piece of equipment. But when we're talking about drones, the sensors, whether it's a thermal, multispectral, hyperspectral, or a red, green, blue camera, which is basically your normal camera you're used to, there's going to be a difference in cost. LiDAR is another sensor that's going to, again, your cost differentiation is going to matter. And what we're going to learn in this course is how do we make the most out of the least expensive sensors? That's really the goal of this course. For one, for you to understand what remote sensing is, for you to learn some of the software associated with photogrammetry, GIS, etc. But in a lot of ways, it's really about learning how to do the most with the least expensive drone, the least expensive sensor. The more you can get out of that, then if you're going into this for a business standpoint, or even you're working for somebody else, you better your efficiencies, the better your effectiveness, and the less expensive it will be. And then the generation of sensor data in the pictures or digital form. So we always want to make sure whatever we're sensing, we're just not leaving it out there, but we're getting some kind of, to use it in the modern era, some kind of digital format back. And you can print it out as a picture. That will allow you to evolve individual photographs into larger kind of orthomosaics, to give you an example. So let's talk a little bit about the data analysis. There are various viewing and interpretation devices. They can be software, they can be visual viewing devices. A picture is an analysis. You can look at a picture, but remember, a picture's not really scaled. So in other words, 1 inch on a picture does not equal 1 inch on the earth, but can we do that? Can we take a series of pictures, and this is what photogrammetry is, and can we come up with something that then allows us to scale that back to the planet so that we can get a real sense of the size and complexity of something. From this, we can get maps, tables, and visual spatial data, photogrammetry, and geographic information systems. So a lot of analysis, and I haven't even touched on them all at this point, but to give you a good sense of acquisition and analysis and how they're two different things. So there are numerous energy sources. So there's visible light, there's the radio waves, there's ultraviolet rays, there's heat, there's X-rays, and in that case, think radar, but in the case of drones, think LiDAR. And again, if you want to capture ultraviolet rays, that's going to be an expense versus just capturing what's visible to the human eye in a simple camera. If you want to capture heat in infrared, thermal, that's going to be a different kind of more sophisticated sensor. And of course, when we're talking about equipping drones, LiDAR is often the most expensive and sophisticated sensor you'll find on a drone. There are other sensors, but normally people don't apply them or attach them to a drone because of the crash factor, and it can become very expensive. Because I often say to people when they ask me, why is this drone so expensive? Well, the drone, the aircraft itself, probably isn't that expensive as much as the sensor you're carrying. But you may have some very expensive sensors, so you may use more expensive drones that have more fail-safes in them to prevent some kind of calamity from happening to your sensor, usually being some kind of crash. So the longer the wavelength, the lower the energy content. So I just want you to be aware of that. For the sake of our courses here at Warren, you do not have to memorize necessarily all these exponentials, but you can see that radio waves can penetrate the Earth's atmosphere, microwave, infrared, a little bit less, visible, those three colors, yes, and then, ultraviolet, X-ray, gamma ray. You get the sense of the size of the radio, the wavelength, not the radio wavelength, but the electromagnetic wavelength there. You get your frequencies, and you get your kind of temperature there as well. So it gives you a little bit of a sense in this chart of what we're dealing with. But what you want to remember is the longer the wavelength, the lower the energy content. So the visible is about in the middle, and that's what our eyes can see. So when we're, again, looking at this, you can see you have some of the atmospheric window, what's emitted by the sun, what's emitted by the earth. All right, so you can't see anything with TV and radio. Microwave radar is going to go through the atmosphere, but again, it's not visible to you. Infrared, not visible. Ultraviolet, not visible. But there is a visible light spectrum. And again, what you're seeing in there is really that red, blue, green, which will contain colors like yellow and purple as well. These images that we can see with our eyes. Okay, so with those, you can use a regular camera, but when you get into things like infrared, you're going to need specialty or LiDAR. That's a specialty sensor at that point. You also need to know that there's absorption and scattering. So all light isn't reflected 100%. So knowing this, scientists, engineers who create these sensors are able to work within their knowledge of the absorption and scattering that goes on and the interactions with the atmosphere to give you a sense of capturing the images in the best way to be used by the human eye later, and to translate those into colors we would understand if we're coming from something like a near infrared or an infrared coloring. So here's a place where you can kind of say, oh, where can I see a great example of this scattering, the absorption? You can go to Google, you can go to the YouTube, you can watch all kinds of things about the northern lights. If you've ever had the chance to kind of go to places like Alaska or there, you might see northern lights and really get to experience them. It's quite a light show. But again, not always the best, not always available to you, but you can see it on the internet as well and get a sense. Let's talk about the reflectance of the Earth's surface, the reflecting curves. So again, you get your blue, your green, your red. Once we get into these ideas of near infrared or mid infrared, they become invisible to the human eye unless we're using a sophisticated sensor. But we can see things like water. We can see things like green grass, and we expect that to be reflected back to us as green. Dry grass may be more in the reddish color. You've seen this in brown during the droughts. the soil, etc. So we can get these kind of curves and we can use them if we understand. And again, you don't need to do this for this particular course or the degree at Warren, because ours is much more application based. But I want you to understand that this exists out here and there are people working on this, studying this all the time. So let's talk a little bit about an agricultural example. And agriculture can provide us some of the great examples of how to use this in the red, green, blue. So what are we looking at here? All right, let's say this is a farm, and we can expect that these kinds of rows that I'm going over right here with the mouse, these are probably those rows, the planting is in between. And when you've seen this on farms, so everywhere it's green, let's assume this is a crop that's growing right now. That's going to be an example of a more healthy crop. You're going to look for greens. You're going to want to know what some of these other colors are. Now, there may not be anything planted here, and you're getting the red. And so you may not be as concerned, but here, this could be telling you something. Why is the growth pattern not there? And depending on the sensor and your sophisticated use of software afterwards, you may be able to tell whether it needs to be irrigated. You may be able to tell whether it needs pesticide. You may be able to tell whether, okay, this area wasn't planted. You're going to be able to switch back and forth from what we would call orthomosaic to this kind of precision agriculture, infrared, multispectral camera taken imagery so that you can see what different things are. So sometimes these could be structures, sometimes they could be water, etc. So, it depends on what it is. But when you're working the farm and you're taking these every 10 days or so, it's going to give you a sense of the growth life. And you're going to be able to really look at what's going on in the world and what's going on in farming. So we have our drone up here. It's capturing and it's telling the farmer everything about that crop. And it can be done in real time using something like Pix4D's Pix Fields. There are numerous other applications that people are using that's going to tell you, okay, here's where you need pesticide. Here's where you're in good shape. Here's where you've overwatered. Here's where you need water. Here's where your crops are in danger. And you're going to get a lot of information. Now, the great thing is a farmer can go out, they could use this information, and they could really have an impact on agriculture using small unmanned aircraft. And in fact, one of the first people to ever fly unmanned aircraft was a farmer from the Midwest who saw drones in kind of a magazine and said, I wonder if I can use those to monitor my crop health. And this has been going on in agriculture for a long time. But when we think about the influx or the increase in population, food production, and how many places on the planet we can produce food, you could see how this technology can do a lot of things. Number one, it can be good for the environment because we may not overuse our natural resources. And it can be great for crop production so that we produce more with less harm to the environment. So you're really starting to see a revolution here in agriculture using unmanned aircraft. So let's talk about some other outcome models that you might get in remote sensing. And again, we're going to focus a lot here on drones and drone technology. So one of the things you're going to see and you're going to be able to produce using a software like Pix4D is something called a DEM, or a digital elevation model. And this is going to not provide you with a picture, but it's going to give you a sense of the elevation. Now, this picture is going to be pretty obvious because it's obviously in a mountainous range. You can tell by looking at it, but we can tell where the water is by the coloration. You can tell by the highest points, by the red, the orange. You may not be able to tell just looking straight at this that the highest point is down here because it might be an illusion to your eyes. But your digital elevation model is going to give you all this information. And this could be very helpful to someone trying to plan out something with this parcel of land or try to understand how things changed over time. There are many ways you can use this, and the application would be to the industry you're working in. You should also know that the digital elevation model can be edited to generate a digital terrain model, which is a representation of both the bare earth model that contains elevations, okay, of natural terrain features, vegetation, buildings, and other non-ground objects are digitally removed automatically, as opposed to the digital surface model, which contains elevations of natural terrain in addition to the buildings, trees, or other objects. So let's take a little bit of a look at this. This would be a digital terrain model. So this can be used to model water flow or other movements, the runs simulated from avalanches or landslides, for land use studies, for transportation system planning, and geological applications. So you can see, you kind of get a sense in this digital terrain model of what's going on. You got the color combinations again, but it will also contain things besides just natural information. So let's look at this digital surface model here as well, and you'll start to see that. You got your water. You can make this out because you got a little bit more of an urban environment. You can see the taller buildings. You can tell that these are smaller facilities, green. And again, you're doing with buildings using a DSM that you were using your digital terrain model for more natural environment. So what happens in a DSM is you're going to capture both the natural and the artificial features of the environment, as you can see here to the right. Another map that can be made, so you got your DSM, your DEM, your DTM, is you can get a contour map from drones as well. So a contour map, or contour lines, it's also known as an ISO line, is a line on a map joining parts of equal height or depth above or below a level, usually mean sea level. That's tend to be a standard that we use. It is often just called the contour. Each contour is a closed curve. The difference in height and depth between successive contour lines is the contour interval. It generally becomes greater and greater when the map scale becomes less and less. So here you get a sense of it. You're not going to see this mountainous area on the map up here. I'm just giving you a sense of that's what it's measuring. So you go, it's going to give you 3,000, let's say, feet, 3,000, 2,500, and you can see these match then as the elevation decreases. So a little bit harder to read, probably a little bit more expertise, but you may in fact just get someone to hire you if you were doing drone work who says, just all I need is a contour map of this area so I can understand the elevation planes that are going on. And you'd be able to create this in matters of really however long it took you to fly an area. So maybe a half-hour drone flight, you can now recreate the contour lines for that person's needs and their planning or whatever their industry need might be. Okay, so we also talk about in remote sensing reference data. So often we need reference data on the ground to kind of match back up to. So it could be ground control points. This is a term you're going to see many times that helps you take any error out of your maps, your models you might get. It may be a reference data that calibrates your sensor so that it's capturing your color combinations as you want. It could be if you're calibrating your LiDAR to make sure that you have your exact altitudes. And then you can use this reference data also to make sure that your error level is less, and that verify that your information extracted from remote sensing data. So reference data is the existing data on the ground that you're going to use to qualify your remote sensing data, make sure it's accurate, make sure it captured what you need, etc. In order to kind of put this on a map or an existing map on the ground, latitude and longitude becomes one of those things that can be captured by the remote sensors and tagged to the photograph or digital imagery or whatever it is you're producing. And so you should know that you're using GPS in the United States, but you may get other satellites that you're using. So Russia's is called GLONASS, Europe's is GNSS, and China's Compass GNSS. And these all exist, and you're going to use this information from these global positioning points. One, to control your drone on its autonomous mission, or when it flies by itself to capture your data, and also to use each one of those photographs will be given a latitude and longitude that the drone believes is correct. Now you should note that there is error here. Think about how much error from the satellite to the Earth. And the good news is it's often because of the atomic clocks in the satellites able to understand the distance, the time, etc. So you're able to kind of compute this error or guess this error, hypothesize the error. So a lot of what we'll do in this course for the most part is go through capturing imagery and then calculating the error and then adjusting and correcting the error, because that's really the key. The key is how accurate can my outputs be for my client, for my boss, for whomever I'm trying to give this information to use, because you want it to be as accurate as possible. And you should also know that when you're kind of getting information, you're going to use more than one GPS satellite. So you need kind of, when you're flying your drone and it's flying off GPS and it knows where it is based on this, the way it can be known is there has to be 3 satellites. Then you can know the position if you have that, 3 satellites. GPS receivers are usually smart enough to choose the location nearest to the Earth's surface. At a minimum, 3 satellites are required for a 2-dimensional horizontal fix. 4 ranges are needed for that 3-dimensional horizontal and vertical mix. The means by which the global navigation satellite system signals are used to determine ground positions is called satellite ranging. The GPS receivers calculate distance to the satellite as a function of the amount of time it takes for the satellite's signals, so those would be waves from the electromagnetic spectrum, to reach the ground. To make such a calculation, the receiver must be able to tell precisely when the signal was transmitted and when it was received. Satellites are equipped with extremely accurate atomic clocks, so the timing of transitions from that standpoint is always known. Your receiver, that GPS receiver and transponder in your drone, is cheaper. So there's going to be error there, and that's what you want to kind of keep in mind. And that's what this course, we're going to spend a lot of time on. We're not going to let us spend a lot of time on the theory of remote sensing as much as we're going to spend time on the application and the correction of error. So if we have 1 satellite, we know that there's a point. We know that it exists, but we couldn't place it anywhere. If we have 2 satellites, then we know that the position is somewhere along this line here. So, but we haven't really narrowed it down at this point. So with 3, we can tell, okay, it might be here or here. So we're getting more accurate. But if we get to that 4th satellite, like right here, and we can correspond all the intersections of all of these at once, then we can have a great sense of the exact positioning on the planet where this goes. So you're looking for 4 satellites when you're getting your information, and the more satellites you have at any one time, the better your accuracy is going to be. So when we're flying at Warren Community College, we enjoy on a regular day about 17 satellites at our location. So our accuracy is often pretty close, because you'll hear things like meters of error. We rarely will experience that at our college because of the number of satellites we have, but we still have error, and error comes from many places, as we'll talk about throughout this. There are ways of dealing with this error, however. So let's say you're operating a drone. Now, if you're operating a standard commercial off-the-shelf drone for $400, that's obviously going to have cheaper or less expensive components in it. So at that rate, you're going to have some issues where you might just have some satellite to the drone, to the receiver, the ground control unit here that the operator can then get, but that's going to give you error. When we talk about real-time kinetics drone, what we're looking at that point is We have a special GPS receiver within the drone. We have a base station accompanied with it. So we're gathering information here to get absolute accuracy, or hopefully within 2 centimeters. We're giving that information to the drone. We're also getting the satellite. You're getting the receiver information. So you're getting a much more sophisticated sensor and group of sensors working together. So you're going to get a greater degree of accuracy. Now we're going to spend a lot of time and even have a video on RTK, PPK, and other mechanisms for improving accuracy. But let's face it, you're going into the drone business and you probably don't have $10,000 to start your business. Maybe you only have a couple thousand, and you got to buy business cards and envelopes and every other thing. So the question is, can we instruct you in such a way that you can use a less expensive drone to get close to the results that you would get from an RTK or PPK drone? And that is in many ways what I see as the importance of this course for you and your learning. Yes, you are going to fly RTK drones. You are going to fly PPK drones. You're going to look at these things. But then what we're going to do when we've captured the information that way is we're going to then go back to our, let's say, Phantom for $800, bought off Amazon, used drone, and can we get, how close to the information can we get that the RTK and PPK drones were able to capture? So as an overview, what if you're like, what is this course really about? Well, we're not going to be launching satellites. We're going to be using remote sensing to capture data, to analyze that data, but at the same time, you're going to be learning how to get the greatest degree of accuracy, because this is an applied course. So let's talk about how the onboard GPS affects the project accuracy. Normally, GPS on a commercial off-the-shelf drone is not very accurate. The inaccuracy of GPS may lead to larger errors in the 3D positioning, the orientation, and even the scale of what you're trying to create. And let's, for the sake of argument, say in your orthomosaic or your photogrammatic output. Therefore, it's strongly recommended to have at least 50% georeference images for an acceptable approximation. This is by Pix4D. So if you're using Pix4D Mapper, all right, you'll see this in the imagery as we go through this course. You'll have these blue dots, green dots, and what you're trying to do is make sure that the camera position that is computed by the software and the initial camera position thought by the drone are accurate. So with enough geotags, more than 50%, and in fact, if you think about it, with our drones, we're going to be much more than 50% most of the time, unless there's something that happened in the connection, which we'd probably refly. But you could end up with the wrong orientation if you less than 50% of your images are tagged or not tagged with some kind of GPS or latitude and longitude. So it's really important that when you're doing this, you remember that you need a certain number of GPS positions taken in a grid pattern. That's how it works. So there's an overlay. Each image you may capture 60 to 90% of the same in the next image. So kind of think of it as you're taking all your photographs and laying them on top of one another to kind of come back to a bigger image of what you're trying to capture. So Pix4D is going to average those global position satellite positions, resulting in a pretty good approximation of the 3D, of the scale and the 3D orientation of whatever you're trying to capture. And they're going to tell you, pick this Pix4D, not me. The optimized position may be shifted 10 to 20 meters due to the atmospheric conditions when the GPS data was acquired. And this is where we're going to use ground control points to increase accuracy. And we're going to do this several ways: permanent GCPs, scaled GCPs. We're going to use these in many different ways to kind of go through how you can do that. And that's part of the course. You're going to know about GCPs. You're going to know about accuracy and error. You're going to know about GPS. You're going to know about global positioning, latitude and longitude. All of this is in the toolbox of the well-educated drone operator. Then once you've done all this, if you're not doing photogrammetry, you might bring this into a geographic information system. So here you're going to find data like points. That could be a person, that could be a building, line, could be roads, rivers, train tracks, areas, census tracts, towns, etc. We're going to be able to match that back with what we've captured. And we can link this data together to really do complicated and sophisticated analyses. So the location data is the geographic data. What you capture, and you're going to link to that geographic data through latitude and longitude, and you're going to be able to apply attribute data to it, or relational database by design. You'll be able to take other databases and apply that to it. So you may really get some in-depth analysis on what you're looking at by bringing your imagery, your tagged digital media acquisition into geographic information system analysis. And in fact, that is so sophisticated, it goes beyond the scope of this particular course, and you will take, if you take the Warren program, you will take another course on geographic information systems itself using drone data. Here's some point data. Now you can kind of make out what this is. I think if you've lived in the United States long enough, you would realize that that is the state of Texas by using that point. Line data, as I said, you can see on a map, you have various lines. So knowing that whatever you're trying to acquire in orthomosaic may be right here, this line data becomes important if you're trying to talk about expanding retail, or expanding industrial areas, or expanding residential areas, or preserving land. These lines and this information that you're going to capture can become very, very vital. And then the other thing we talk about is often called polygon. And so you can see here, by taking census tracts, you can look at obesity rates. You can look at an obesity density model, and census blocks down here, even smaller than tracts or school zones in this case. You can really get in and say, okay, where's my issues? This is all stuff you can do in GIS. It may be helpful to kind of look at things from an aerial orthomosaic model as well, bringing in that data, because there may be something about what's going on in particular geographic areas. If we knew what the ground looked like, if we knew what was going on there, is it urban? Is it rural? This we would not know by looking at the map, but these are things we can certainly identify later. And you can pull all these things together at once to really get a sense of something that might be going on, a phenomena that's going on in the society. And sometimes what might be helpful is to come down here and click on like one of these little points and maybe pull up an orthomosaic or some other remote sensed information that, again, adds complexity, adds understanding to whatever it is we're trying to analyze. You know, again, when we get into these things, giving you hypothetical examples is really not great, because there's probably so many examples that we could give. It's really a matter of the imagination of how you want to use this. So we'll use in this program, I've talked about Pix4D. We use Pix4D Mapper. You'll learn in remote sensing Locate, which is search and rescue. You'll learn Pix4D Fields, which is an agricultural-based product. We will work with Pix4D React, which is more one for law enforcement. And you'll also work with Drone2Map, which is really Pix4D, but it's another program that's used with ArcGIS or ESRI's product to really make just bringing it all together much easier. If you can use Pix4D Mapper, you can use Drone2Map, because again, the only thing that changes is the graphic user interface. So let's talk about this. I've talked about photogrammetry. I've talked about imagery. I haven't really defined it for you at this point. And so let me do that real quick. And I apologize, for some reason PowerPoint wants me to start over again and again. Maybe it knows how many times I stumbled over my own words here. But let's talk about photogrammetry. Enough about me. Photogrammetry is the science of making measurements from photographs. The output from photogrammetry is typically a map, a drawing, or a 3D model of some real-world object or landmass. So in our picture example here, we might be going over a construction site. We might fly the entire site. Okay, so each one of these little images here would be a picture taken by the drone. There would be where the drone thinks the camera position is, where Pix4D is computing that the camera position is, and your goal is to bring these two dots together because that's going to give you your accuracy on the ground. And you can do all kinds of things. You can take volume calculations, you can map progress, you can look at the land, you can look at water flow, you can look at the terrain around, you could look at elevation, lots of things you can come here. But here's kind of the point. One picture from above is a picture. Taking all these pictures together and bringing them together using GPS data and overlapping pixels is going to give you a model or a map that will go to scale. So for instance, 1 inch on this picture, you'll never know. A lot has to do with how high were you, how close to the ground, how much area did the pic. You'll never get scaled with it. But all these pictures together can bring you accuracy in scaling, which would then allow you to be able to measure precisely what is on the ground. So you would know what 3 feet, it would be exactly 3 feet. And again, the goal for surveyors is to get to about 2 centimeter accuracy or 2 centimeter or less error. The goal for you and your client may be very different depending on what the purpose that you're trying to accomplish is. So it may not be a 3D map or a map of the ground. So you can create this from aerial photogrammetry. The camera is mounted on the drone and pointed vertically towards the ground, and otherwise known as a nadir, pointing straight down. But you can also use photogrammetry, and you can use drones to create 3D models of monuments or statues. And here the camera might be on an oblique or horizontal on the unmanned aircraft vehicle. So let's take a look at how drones have been used to capture and scale the Christ the Redeemer statue in Rio de Janeiro. This is an important cultural icon. Imagine if something happened to it, could you recreate it by capturing every aspect of that statue with a drone and bring it using photogrammetry? You can literally create a model that will hold digitally the information about that forever. So you can maintain, it will help you with reconstructing it. It will help you with moving through and rebuilding it or fixing it or adjusting. So let me have you go to YouTube, and then search within YouTube, mapping Christ the Redeemer. And what you should see is a picture like this. It's only a 2 minute, 53-second video. And you're going to see an Aryan drone, which is a very nice drone, and how they worked with the local people and local government agencies to really model very precisely in Pix4D the Christ the Redeemer statue. Go ahead and take a look at that image or that video for a few minutes, and then we'll reconvene in a second here. Well, welcome back. So let's talk a little bit about Warren Community College to give you a sense. So this is a orthomosaic 3D map captured with the Wingtra drone. Okay, so highly accurate drone. We were able to actually apply PPK technology, although I did not in this image that I've created. You have the college facility. You have the drone port here. You have our drone race course here. You have our wooded area where we do search and rescue over here. And parking lots, we do volume calculations on this. Here's this little piece here is the accident reconstruction area and electrical wire kind of practice area, and then a lot of flight practicing in here. But we're able to capture everything in this image, and this is to scale now. It's not just single picture. This is hundreds of pictures tied together and overlapped. So we have multiple overlapping photos with 80 to 90% overlap. That's a lot of overlap. of the ground or model are taken as the unmanned aircraft vehicle, which was the Wing Chun 1, flies along an autonomous program flight path called the waypoint. So it flew a grid pattern, taking a picture, and it's a fixed wing, so it does more of a kind of, it's not quite like a horizontal or a VTOL, because it doesn't go in a square pattern. It takes off, vertical takeoff and landing, and then turns into a fixed wing. So you're getting a grid pattern around the property, basically like this, and then flown like so. And so you have this amazing amount of overlap, which again is going to tie all those pictures together into one image, which here would be a 3D map. To overlap photos of an object or land by 80 to 90% would be impossible to complete accurately by pilot navigation. So in other words, if I was flying this with remote control, you know, the 2 sticks on a drone, I would miss too much. So what we use is waypoint technology and autonomous pre-programmed mission routes. Another thing we'll learn in our program here in almost every course, but we'll very much concentrate on it in this course. So be aware of that. So this is from the Pix4D website, and it just gives you a sense of the image shooting rate to achieve a given frontal overlap depends on the speed of the unmanned aircraft vehicle, the ground sampling distance, and the pixel resolution of the camera. So all these things matter. So your level, think about your level of error that can be diminished or increased. Will have all kinds of things, not only your GPS positioning, but your overlap, your distance covered, your distance between 2 camera positions, your flight speed, how good your camera is, how many megapixels it has, how high your altitude, that's your ground sampling distance. And so you're trying to get to the ideal, and that's one of the things we go over in this course. Again, this is an overview. We'll spend about half a day on this slide alone and explaining it. Because we're using an applied degree and not a engineering or a more theoretical degree, we're going to be attacking this information from a very practical standpoint. So let me give you some more about what we'll be talking about. So for precision agriculture, we'll be looking at things like indexes, like the vegetation index. We'll look at things like orthomosaics, surface models, prescription maps, and we'll get a lot of information about this. Again, if you go to YouTube and you type in Pix4D drone mapping for digital agriculture, you'll get a good indication of how this is done. And I suggest to you go back to YouTube and watch some of these videos as well. But before we do that, let's look at this one. I want you to go to YouTube and search principles of remote sensing and mapping using drones. So YouTube, principles of remote sensing and mapping using drones. So in about 2 minutes and 46 seconds, you're going to get a sense of this from this video. You'll see some remote sensing done. This will focus in, unlike the other videos, mainly on the use of drones for creating a map. So you've seen the drones remote sensing for a 3D model. So this is an example. I'll give you some sense of how to use drones in mapping. All of these things you'll learn in this course. So as we move forward, let's talk a little bit more about our overview of our course here. What you have to realize is a lot of our missions will take place here in Warren County. So we will do various mapping missions. We may map farms that exist, private farms. We'll map college land here, and we may map over here, off the map a little bit, up here probably, amusement park like the land of make-believe. So in our program, we have access to a number of places. Another one where we often go is to the Morristown Airport, because a lot of our faculty work at the airport as well, so our students get to go to the airport. Now here's kind of the good part. Here you'll end up working with air traffic control and learning that as you do remote sensing work. At the amusement park, we may use our waiver to fly over people so that we can map that while it's active and create promotional stuff as a kind of assistance to them and a thank you for letting us use the park. At the farms, we'll go over precision agriculture and everything we can't do that, whether it's accident reconstruction, search and rescue, we will do at the Smith UAS Flight Training Center here in Washington. And as you can see, if you remember from your Part 107 lessons, this is an ideal location in New Jersey, one of the few places in New Jersey where the airspace is pretty clear. So your Class G up to 1,200 feet here, because we're outside of any of these magenta circles. And we're at a nice place here. There's a couple of private airports around that are well aware we're here. There's some things we can do. There's a burn building here. There's the college facilities. There's a lot here where we can really get into remote sensing between our partners and our property. We're able to do a lot of missions that other students might not be able to do because you can't get access to these places. So this is part of our program to get you out there as much as possible, flying missions, both at the college where you'll start, and then in secondary locations that are industry specific with our partners that we have. So here's a sense of a mission map of over top of the college. Here's the college parking lot. Here's the Warren County Tech School here. And you could see that this was taken by the Wingtra 1. And a tremendous number of photographs in grid format over this area. So we're able to capture a lot of overlap. And so each one of these red circles represents a picture taken by a drone. And you can visualize here the amount of overlap that you'll see. All right, here's the same, but this is the number of pictures. So you can see this is quite a few pictures over the property. We went over some of the wooded area, over the college area, a little bit over some of the road parking way when no one was around. But this is what's known when you get into Pix4D as the DRONEPORT. This is the point cloud. So you'll hear that term and we'll go over that again so many times. By the end of the course, you'll be like, I can't believe I never knew what a point cloud was. So here's the point cloud when we take off the rays and we take off the photographs. And so what we have here are unique pixels that the software has identified. And you can see here in the kind of open area with different color variations in the facility, it looks pretty remarkably, lots of pixels. When we get over here into this foliage area of the wooded area where everything tends to look the same, you can see less pixelation over here in the point cloud. That tells us something. It tells us about when we want to process. We might have difficulty processing all of it because there's less pixel differentiation here. And this is one of the things we'll talk about and we'll fly missions. One of the ones we'll do in a fall semester is fly a local corn maze. Well, the corn has died, everything is brown. The maize part is there, but it takes a tremendous amount of kind of understanding of overlap and ground sampling distance to get pixelation and differentiation in those pixels in something that everything looks alike. So we walk through those, we work through these hard problems for you so that when you go out and you're applying this knowledge in the field, you have some experience already. This is what's known as the densified point cloud, where we kind of take the points and then triangulate to understand. And you can see it starts to look more clear at this point. Now, this is your 3D textured mesh of the DRONEPORT. And you can see at this point, you have a really good, now this is all taken from a vertically straight down, 0 degrees, known as nadir camera on the Wingtra 1. It cannot take horizontal imagery. So you'll see some, if you look really closely here on the sides of the building, there's always some kind of lack of ability to process that. We go over, how do you then take a drone and fly a circle around and fix the sides? How do you take a land camera with GPS coordinates on it and overlap so that, again, then you have some understanding and you can fill in the sides of the building, making yourself almost a perfect model. So some of the things we do in this course is we learn about pixels. No, we learn about remote sensing. So we want to go over that first. We learn about the electromagnetic spectrum. You're going to learn about pixels and what you can do with them. You're going to learn about error, GPS error. You're going to learn about how to correct all these errors, how to adjust your missions to fly the best mission possible, how to use other technologies, how to integrate other pictures and imagery into it to correct. So a lot of what we're doing in this course, after we learn the basic theoretical information, and again, because this is an applied degree, we're not really going in depth into the theory behind all this as much as we're going into the practical application. So, okay, this all looks the same. I didn't get a lot of pixel. How do I correct that? What would I need to do? How would I need to fly that? How do I correct the sides of the building that are all kind of distorted because I took all the pictures from a straight down camera from a drone? That's part of the course. How do I use ground control points down here to correct my image to 2 centimeter accuracy? Okay, I don't have ground control points at every job. How do I use temporarily placed cheap, less than $100 GCPs to scale my image and get that accuracy back? These are all examples of the kinds of things we'll be going through in this course. At the same time, you're going to make orthomosaics. You're going to learn about digital surface models. We're going to show you different things that a client may desire from you, how to interpret, how to read this, how to read precision agricultural maps are something we'll go over. All right, and you'll also learn how, and probably most importantly, how do I bring this into other software? How do I bring this into a GIS software? How do I bring this into CAD? How do I bring this into something else? And you know, one of the simplest ways is to create what's known as a KML file that will go into Google Earth, and you can take then your satellite images and overlap and place on Google Earth. And you can kind of then see your level of error. This is one of my favorite ways to kind of see error, because you can see when we put this on the map, we put this on the satellite taken image from a drone images that maybe were taken from using the Wings Run. I'm going to guess at that day we were probably flying at about 200 to 300 feet, somewhere in that range. And what's the level of accuracy? Well, you can kind of see here, very, very close to what is on Google from satellite imagery. But remember, that satellite imagery could be wrong. So even though this road here might match up, we could still have error from both. So we could have equal amounts of error. So again, what we're going to go over in this course is how to use these different technologies to bring things in and out of software that other people might use. Remember, everybody you're going to hand something to isn't a drone expert. They're not a photogrammetry expert. They're just trying to get a product that they can use to do whatever job they're trying to accomplish. So we're going to teach you how to create a number of these outputs so that you can give your client what they want, which is why our class on photogrammetry takes a semester rather than 3 days, because we're going to leave you with a tremendous amount of expertise, not the least of which is take you through so many exercises in Pix4D that you would be comfortable and able to sit for their Pix4D certification exam. So you not only get a degree from us, but you get certification as well. That's the goal of the overview of the course in our program. Next week, we're going to get into some more serious or more practical on photographic systems and sensors. So we're going to go through what are some of these sensors that are available? What are some of the sensors in my drone? What are some of the photographic systems that I can pick from? And remember, when you call a vendor, they're always going to, you know, they're going to try to sell you what you need, but they may try to oversell you a little bit too for your next job. So what we're going to do is give you the education that you need to understand what to buy, but more importantly, what you don't need to buy, so that you're not spending money on things you don't need for your either employer, or if it's your own business, from your own pocket. So we look forward to seeing you in the next video. Take care.